Hi everyone, we're continuing with lesson 18 on binomial distributions. And last time we really focused on this one particular distribution, this binomial distribution where n equals 5 trials and success probability p equals 1/6. This is the distribution in tabular form. And we saw applications of this to rolling dice and counting the number of fours, to the cooties example, where we took 5 random Americans and counted the number of cooties cases, and the multiple choice test with 5 questions, each A through F. The student guesses randomly, and we count the number of questions the student gets correct. Actually, we can modify the coin situation for this distribution. Now, in the usual situation, we have students flip a fair coin 100 times. A head is a success, and X counts the number of heads or successes. Then X has a binomial distribution where n equals 100 flips or tosses, and success probability, head probability, P, is 1/2 or 0.5. So let's say that P is 0.5, the probability of heads. We have n equals 100 flips or tosses. This student gets 51 heads and 49 tails. We see a dot at 51 on the dot plot. Let's say that 1,000 more students join in the fun, do the same thing. Student number 1001 gets 52 heads over here. And here is a frequency histogram for the number of heads, the value of X, obtained by the 1001 students. Now, what would the corresponding binomial probability distribution predict in terms of the frequency histogram? It predicts what's in green, which is a pretty close model for what we actually see in our simulation. Now, this green histogram is given to us by this distribution, a binomial distribution where n equals 100 and p equals 0.5. That's the ideal theoretical distribution in green. Now, what happens if we consider this alternate distribution where n equals 5? We're just rolling 5 dice or flipping 5 coins here. But this time, the probability of success P is 1/6. So we're modeling rolling 5 dice where we're counting the number of fours, or we're flipping a very unfair and biased coin where the probability of heads is 1/6, not 1/2. So let's say the probability of heads is about 1/6, about 0.167. That's the decimal equivalent rounded off. Okay, 5 flips or 5 rolls of a die. One sample. Let's see what happens with one student. Now here it looks a bit different. So basically, it's like a student rolling the die 5 times, or rolling 5 dice, or flipping a biased coin 5 times. So each of these wheels here corresponds to a die roll or coin flip. Now, 1/6 is the proportion of each disc that's blue. That corresponds to a success. So if the spinner lands in the blue wedge, that counts as a success. For example, here, this barely counts as a success. The spinner barely enters that blue wedge. That counts as a success, which means that the die came up a 4 or the biased coin came up heads. But in these 4 other rolls or flips, the spinner landed in the pink area, which corresponds to a failure, or 5/6 of the pie. So we had 4 failures over here because the spinner landed in the pink failure pieces of the pie. So among these 5 die rolls or coin flips, we had 1 success, just barely, and 4 failures, 1 head and 4 tails, if 1/6 is the probability of heads. Now what happens if we do this? Let's turn off the binomial. Let's say that we do this 1,000 more times. Notice that the dot here indicates we had 1 success for this one student rolling 5 dice. If we have 1,000 more students, here was the result for student number 1001. Again, 1 success. Okay, so it looks like we have a bunch of students who got either no 4s or 1 4, fewer students with 2 4s, even fewer students with 3 4s. Or in the context of coins, remember, it's a very biased coin where the probability of heads is 1/6. We had many students who got no heads, many students who got exactly 1 head, fewer students who got 2 heads out of the 5 flips, fewer, fewer, fewer. Okay. By the way, what does the binomial distribution over here predict? The binomial distribution predicts this frequency histogram over here in green. So again, the binomial histogram, or really the frequency histogram predicted by the binomial distribution, does a very good job of the actual frequency distribution we see for the 1001 students. Okay, so here again, we're looking at a twisted or biased coin situation where we end up with the same binomial distribution as this guy over here. And what we see is what we get. I mean, in terms of the actual simulation, we get a frequency histogram that's very close to what the exact binomial distribution predicts for us. All right. So now, back to these notes. Now, fortunately, the notes that are primarily handwritten, these will not be on the homework or the exam. This describes how the probabilities are computed. I'll discuss these in later optional videos. Now, what's still required? Well, first of all, we have the sampling rule. Remember, when we had the cooties example, we were drawing a random sample of 5 random American adults, I guess, from the overall population. And by the sampling rule, we could still assume independence. We could still have a binomial experiment because because the sample size, little n, was tiny. It was only 5. And it was certainly no more than 5% of the overall population size of American adults, which is in the millions. Okay, so we could assume independence. That's a side note. What else would be fair game for homework or potential exams? Well, let's say that we have this example here. Example 2, using tables to analyze binomial distributions. Let's say that 70% of American adults like Senator Smith. That is, the probability that a random American adult likes Senator Smith is 0.7. Bear in mind, there's often a direct relationship between proportions and probabilities. 70% of American adults like Senator Smith, that's a proportion. That's readily translated as a probability. The probability that a random American adult like Senator Smith is 70%, or 0.7. There's often a relationship between proportions and probabilities. Now let's say that 6 American adults are randomly sampled to form a focus group, and we want to ask them questions about Senator Smith, their opinions of Senator Smith. Find the probability that at least 4 of the people in this focus group of 6 like Senator Smith. Big hint, we have this table here. Now, on an exam, it's fair game for you to be required to know that the distribution we're talking about is this distribution. If we let X be the number of people in the focus group who like Senator Smith, then X has this as the distribution. A binomial distribution where n equals 6, that's the number of trials, the sample size, the number of people in the focus group, and p equals 0.7, the success probability per American adult. Now, we're saying here that a success means that an American adult likes Senator Smith, and we're counting successes. So x, the number of successes, can be an integer between 0 and 6. And it turns out that these are the corresponding binomial probabilities. Now, on an exam or a homework problem, I would give you this table of probabilities. Later on, in optional sections of videos, I will discuss how these probabilities are actually obtained. But for homework and or exams, I would actually give you this probability table, this probability distribution table. It's the table for this distribution. Okay, so the probability that nobody in the group likes Smith is almost 0. Bear in mind, Senator Smith is pretty popular, and the probability that nobody among the 6 people in the group like Smith is almost nothing. Now, 70% of American adults like Smith, it's not surprising that the most likely number of people in the group who like Smith is 4. 4 out of 6 is pretty close to 70%. 2/3 is pretty close to 70%. The probability that exactly 4 people like Smith is 0.324. After that, the probabilities go down. The probability that all 6 people like Smith, it's lower, 0.118, but not terribly low. Senator Smith is very popular, and the probability that all 6 like Smith, it's not too low. It's lower than the probability of 4 liking Smith, but it's not that close to 0 either. Okay, so given this probability distribution table, my question here was, find the probability that at least 4 people in the focus group like Senator Smith. So this is similar to what we've done before. What's the probability that X is at least 4? Basically, we're focusing on these 3 rows of the table, and we want to add these probabilities. Remember, at least 4 includes 4, so we want to include this probability. And we also want to go higher. We also want P of 5 and P of 6. In the end, we want to add P of 4, the probability of exactly 4 people liking Smith, P of 5, the probability of exactly 5 people liking Smith, and P of 6, the probability that all 6 people like Smith. We're going to add these probabilities. Again, these probabilities are fairly high because Senator Smith is popular. The probability that X is at least 4 is P of 4 plus P of 5 plus P of 6. We add up these 3 probabilities, we get 0.745. So about a 3 in 4 chance that at least 4 people in the group of 6 like Senator Smith. And that would be fair for a homework or exam question. So afterwards, we're going to deal with basically optional videos where I'll discuss how these probabilities are computed. But we're going to talk game shows, and we're going to have fun as well. I'll see you later.